Okay. So, maybe for these matrices, maybe for others, you got Bx equals C. Okay? Now we know that B is invertible because it has non-zero determinant as we determined from the LU decomposition. We would have never gotten to the upper lower triangular decomposition if the matrix was singular. Okay? Because we'd have ended up with a row of zeros just trying to get down to the upper. Okay? So, we have this. Now, so our strategy is going to be to solve Ly equals C. Okay? Then we're going to solve Ux equals Y. Okay? In other words, we find what you have to multiply by L to get our C. And then that's what Ux has to be equal to, because that's what L multiplies to give you C. Fairly simple idea, right? Okay? Make sense? Okay, well, that's pretty easy to do. Okay? Just for an example, let C equal 1, negative 1, 4. I've been wanting to write down that column vector for months. Finally feel okay. Not sure. Okay. I feel okay, but not because of that. Not that okay, you know, but kind of okay. Okay, so we've got Ly equals C, means that for our matrices, L is 1, 0, 0, 2, 1, 0, 3, 2, 1, yeah, 3, 2, 1, times Y1, Y2, Y3 equals 1, negative 1, 4. Okay? Well, we're just going to use forward substitution. Doesn't this first row times this tell us that Y1 equals 1? Okay? So I can write out the system. Okay? That, I said Y1 equals 0. I don't know why I would have done that. But because I have zeros here and I was thinking about those coefficients. Okay? So, well, if Y1 equals 1, then 2Y1 plus Y2 Y2's got to be negative 1, right? Okay? So now, Y1 is 1, Y2 is negative 1. So that this adds, this adds up to 4, so we get this. And I don't have to read it to you. So Y3 is what? Well, that's 3 minus 2, that's 1. Subtract 1 from both sides, Y3 had better be 3. Okay? Now, at this point, you do want to check, especially when you're first doing it, until you get a lot of confidence. So you just take the vector 1, negative 1, 3, and multiply it by this, and see that you get 1, negative 1, 4. Okay? Now, assuming that's right, we see this. So that's what L has to multiply to give you this vector. then ux equals 1, negative 1, 3. Well, U is another triangular matrix. It's upper triangular. Where is it? 1, 2, 3. 0, negative 1, negative 7, and 0, 0, 7.
I feel like I did this wrong.
Let me finish writing this out and then we'll see what. Okay, what I screw up?
I probably did. Because I ended up with 1, negative 3, and 7.
1, negative 2, and 7.
1, negative 3, and 7.
1, negative 3, and 7. Let's see. The U I get here from.
It's
You turn it against the L.
1 is 1. Subtract that.
Oh, you say in solving this thing, I get a negative 3. Well, if y1 is 1, then 2y1 is 2. So 2 plus y2 is negative 1, and you're trying to tell me, oh, this is a negative 1. Okay, thank you. This is negative 1, I didn't write down the negative sign, and this is negative 3. And that's going to change this, because that's 2 times negative 3. That's going to be negative 6 and 3, so it's going to be negative 3. And if I add 3, I get y3 equals 7. Which is good, because I got 7s up here. Okay? Thank you, good save. So that's negative 3. And that's 7. Okay. So, what do we see? Well, this row says 3x3, 7x3 equals 7. So x3 equals 1. And then negative x2 minus 7x3 equals negative 3. So x2 equals 1. Well, x3 is 1, so that's a negative 7. So I'm going to have to add 7 to negative 3, which gives me positive 4, but that's negative x2, so x2 should be negative 4. Okay? Again, check me. And then we have x1 plus 2x2 plus 3x3 equals 1. So x3 equals what? Well, it's going to be 1, and then minus x1, which would be minus 1, which is 0. And then minus 2x2, which is minus 8, which is plus 8. So I think x3 is 8. Okay? Now let's just check that, because you're less likely to make a mistake here than I am. So we can have the adventure of my having made an error, which is not unusual. So let's check and see if this is really a solution. So the matrix is 1, 2, 3, 2, 3, negative 1, and 3, 4, 2, multiplied by 1, negative 4, 8. Is that equal to the C that we had here, 1, negative 1, 4. I think there's a 50-50 chance. Okay? If not, then I'm back to the drawing board. But I'm not going to go back until you go back. Okay? So we have 1, negative 8, positive 24, nah.
Makes 3 equals 6.
Huh?
Makes 3 equals 6.
Still not going to be good. So something went wrong and it shouldn't have, but okay. x3 is 1. Oh, wait a minute. I let x1 be 1. Okay, hang on. x3 is 1. So x2 is negative 4, so that's all right. So now I've got negative 8 there. plus 3, yeah, you do get 6. But it's x1 equals 6. And I did these in reverse order. And look at it carefully. So, this should be 6, negative 4, 1.
That's what I got.
Huh?
That's what I
Yeah.
got.
Yeah, I just wrote it down wrong. Just looked at that column and wrote it down. So be careful like I'm not. Okay, so we get 6, negative 8, okay, which gives us negative 2. 3 times 1 is 3. That adds up to 1. Okay? That's 12. That's negative 12. And that's negative 1, so there we got it. This is 18. Negative 16 is 2. And 2 is 4. It worked. Okay? As soon as I wrote these down in the right order. So I've intentionally made some mistakes so you know what to look for, right? And you know to be careful, but this demonstrates the idea, and the central idea is once you got the LU decomposition, you let y equal ux, and you find out what you got to multiply L by to get C. You can solve that by just simple forward substitution. Okay? Then once you got that, well, that's what you got to multiply by u. Or that's what you got to get when you multiply u times your x, so that when you multiply L times ux, you get C. Pretty straightforward. Okay? Then it actually worked out. There's a couple little corrections that you guys caught. Okay? That's a lot less work than reducing the entire matrix. Okay? Now, not so much for a 3 by 3 matrix, but starting with a 4 by 4, it's a lot less work to get upper triangular form than it is to get the Gauss-Jordan form. Okay? And upper and lower triangular equations with upper and lower triangular matrices are just a matter of forward or backward substitution. Solving equations. Okay? So, it's a pretty powerful technique. There are other decompositions. This is the first one you've seen. Puts a matrix in a form that makes things much easier to deal with. Okay, and if you're writing a computer program to solve a matrix equation with 10 by 10 matrix, okay, you would much rather do this than that. Okay? You know, how many steps does it take to reduce a 10 by 10 matrix to upper triangular form?
I think it was in the
Well, it
book.
takes 1 step to get the second row, 2 steps to get the third, 3 steps to get the fourth, okay? So it's just 1 plus 2 plus 3 up to 9, okay? Which is 10 times 4.5, which is 45 steps, okay? And then you have, you got to do your inverse matrices and stuff. If you do the entire decomposition, how many steps do you have? You want to compare that, okay? So there's an efficiency advantage here. And when you're doing computer algorithms, if you do computer algorithms, you want these kind of decompositions. You also got this SDV decomposition, many others. Don't think we can really talk about it in this course, but you're decomposing it based on your eigenvalues and eigenvectors. Okay? It's a spectrum type decomposition, I think. I have to think back through that one. Because I don't exactly remember what it is. I've not done it much, and I've not used it. But you got spectral decompositions where you decompose things according to eigenspaces and stuff. Okay? They're all extremely powerful, extremely important. Okay? So this is your first step in matrix decomposition. Pretty much the only step we're going to make in this course. It's something you can kind of anticipate if you get into a field that actually does this heavily, and if you don't, well, it's still kind of neat to know. Okay?